like I said, we're going to look at some real data, see what we're able to observe, and what we're able to learn from it. The really simple background on what we do is, it's an inline camera. It scans left to right, or in the transverse direction as the material goes underneath it. We then have an edge box running a couple of GPUs sitting right alongside the camera, and those are crunching the data in real time to extract some real parameters from each image. Um, the the equipment looks something like that. We've had it, like I said, mounted on. I think we've had it mounted on 4 or 5 different lines so far. It's relatively easy to deploy. It does need to sit on top of a roller because it's fundamentally a microscope. It does have autofocus, but it can't track a an electrode that's not supported. It would just go out of focus. Really quick overview. We call it OMM, Optical Measurement Module. Our company is called PDF Solutions, so we need to put a 3-letter acronym into everything that we do. How is it different from traditional systems? The biggest thing is the resolution. So two micrometers roughly versus 50 micrometers if you're using a traditional system. What that lets you do is it lets you get some kind of data from every single image. And then in order to, and that in itself gives you two other things. So that means we will see features every time we take an image. And those features are actual real things, where they're objective rather is maybe a better way of putting it, right? So NMC is a really easy example to talk about. So in NMC, we can observe basically every single grain in every image, every single void in every single image, and we can quantify the size distribution again in every single image of those two features. We can quantify if some of the material is sufficiently out of plane that we're losing focus. We can also observe any kinds of impurities, and at this point, quantify whether they're metallic or metallic organic, or sort of some sort of ceramic that we're not expected. All of this being done with AI and visual standard colored images. The downside of all of this, of course, there's always a downside, is because the resolution is so high and the data volume is so high, we can't do 100% inspection. We do statistical inspection, which means if you're looking for like a 1 in a trillion fault, we're not going to catch it. But if you're looking for a 1 in a billion kind of fault, we're more than able to catch it. It'll just take us, I think, something like an hour to capture most relevant PPB kind of failures. Case study so far, yeah. So let's get into it. So this is going to be, we're looking at LFP pouch cells. The instrument is located on the anode after slitting, and the total amount of data that we've collected here so far as of today is so a little bit over 1 million images collected over 30 days. We're not collecting 24/7, just because this particular line isn't running at full capacity, and we'll be looking at a little bit of a subset of that data. I'm not going to load 1 million images. So maybe just to get started, here are some sample images. Some of the things that we see, we've got, this one on the far right is kind of interesting. You see these black stripes that recur on the roll. We're not quite sure what those might be. We see definitely contamination. These really light colored, relatively large particles, which you see an example here and another example here, which is something we're going to spend a fair bit of time talking about. And you also see sort of differences in the void structure, which you can see in the image on the far left. So when we spoke with the client, their primary worries were about they wanted to reduce their high pot failure count. They weren't sure why they were getting these high pot failures. They thought there was some sort of copper contamination. So what we did is we had an out of the box algorithm that was looking at impurities. That's what we ran on here. It tended to actually detect not just the large metallics, which you can see in these green boxes, but it actually kind of triggered off of graphite cleavage as well, which was this proxy for surface roughness. It was interesting to us immediately when looking at these things that one, we basically didn't see any copper at all. And two, what we did see is, we've done a bunch of these things. What we did see looked very much like aluminum, and in quantities and sizes, which were definitely very worrying to us and were worrying to the customer once they saw them. So this is a plot of, let's call it large aluminum-like particles for some of the data, and what jumps out is there's a definite correlation between these large ones. So these are particles roughly 20 micrometers in diameter, and the occurrence of high pot failures in that specific batch. So the customer saw this, and I think two things happened. One, what I mentioned earlier is they had really expected copper contamination, and we went back and forth a bunch of times. We're like, no, there's no copper. And so once they got on board that it's not copper, that it's aluminum, then they were able to actually start looking for root cause and knowing what to look for. Oh yeah, if anybody has questions, just jump right in. It's such a small room. Just speak up.
Well, so how do you know it's copper or aluminum? Can you do correlated spectroscopy where you capture an image or mark it somehow so then you could run it to semi-DX or XRF and say this is exactly what it is for the
You
same identical particle?
you could. It's expensive. It's much. We've looked at a bunch of this stuff previously, and basically, if we're talking about copper, the idea here is that the copper is coming off of. So this is anode, right? So that it's coming off the carrier metal, let's call it, off the foil. And because these are color images, it's actually incredibly straightforward to distinguish between copper and aluminum. All we have to look is at the color, and if we're not seeing any red or orange, all we're seeing is this bluish white. It's pretty easy to say, hey, that's not copper. And then again, based on our experience looking at aluminum versus steel, again, there's a in most cases there's a pretty obvious difference in appearance, mostly coming actually from shape and almost texture, where the aluminum particles that we've seen in cell manufacturing are, it's more malleable, and you can actually see the edges are softened, versus anything that we've seen in manufacturing, which is coming off of steel, is a lot sharper. So to kind of close the loop on that question, yeah, we could we're tracking position, so we could, stop the line and cut this little piece out and take it, ship it over to SCM, and then, spend however much time trying to find it. It's always a little bit tricky to get within that final 100 microns. But this is definitely not copper, just based on the color.
Yeah,
Does that make sense?
that's a big particle when they get smaller. So what's the smallest size particle that people are worried about shorts or other issues?
About 20 microns would be it.
Okay. Okay.
Yeah,
Yeah, I'm more for semiconductor industry on average. So
yeah. Um, yeah, I mean, we can detect the smaller stuff, as an indicator of issues. That's effective, but in this specific case, their problems are uh, so big, or maybe so far along, that they're looking for the big ones first to show, hey, is this what's driving our failures? And in that case, those particles need to be basically bigger than the thickness of the separator. Yeah, so what happened here is, the customer said, oh, okay, fine. So aluminum. So let's go back to the machine and look for sources of aluminum contamination. They were able to find something. They did, on the left here, you can see them trying, once they had the most likely source of the contamination, they did some surface sampling. Yeah, sure enough, aluminum contamination, and then they implemented basically preventive maintenance, which is periodic cleaning, with the idea that, a system like ours would tell them, is this the one and only source, and has this been effective, and how often do you need to stop the line, and how well do you need to clean this thing in order to make sure that your particle counts are way down. So I think what we found is their initial cleaning procedure, I think, reduced the aluminum particle count by something like 40%. And we're now working with them to see if we want to drop, if it's worth it to drop that further. So yeah, moving on to use case two. Use case two is not as straightforward. So use case two is still open. So this is the self-discharge coefficient for a series of batches. So we're looking at 26 different batches, and that's an awful lot of variability, which will then impact how difficult these things are to integrate into at the pack level. And so the customer wants to have as little variability as they can, and ideally they also want to have low numbers wherever they can. And you can see that, right? And in some of these cases, these are pretty significant differences, right? We're looking at over 20% difference in self-discharge. So if they can figure out what's going on and control their process so that the self-discharge is around the really low values consistently, then that makes their product more valuable to the end user, and they can improve their margins, increase their costs, et cetera. And so what we found here when we looked at our data, so this is image data, and now we're looking at kind of a proxy for surface roughness. So we're looking at those graphite cleavage sites. And we observed two things immediately. So one, there's a periodicity in this, which looks like wear on their calendar equipment, which you can see on the figure on the left. And there's also step changes, probably caused by issues in the coating or slurry dispensing system. And where we are right now is we're building basically a process where with the customer, we try and identify, okay, well, what are some potential root causes? what can we do to how much of this data collection do we need to do to be confident that we've really identified the root cause through like a natural design of experiment, and then they are able to, adjust the process parameters upstream, and then we'll be able to tell them if those adjustments were effective in reducing this variability. And essentially, right, this is just a way of ensuring process repeatability for all of the upstream processes using a single instrument that's mounted, essentially right at the end of all of the anode processing. So, this is kind of where I thought we could pause and chat a little bit. I've got some other slides about what we do, but I think that's the interesting part. So I'm curious. Yeah, I'm curious at this point what you guys. Oh, hey, Michael. If you guys have any thoughts or insights on similar problems that you've come across, and honestly, some different ideas that you would approach the process variability question, or yeah.